Good afternoon, good evening, and good morning to all the participants who have joined us today in the webinar titled Making the Invisible Visible Technologies for Groundwater Management. Myself, Afia Siddiqui from IWA, and I'll be moderating the session today. Next slide. So just a few housekeeping rules for our participants today. This webinar will be recorded and it will be made available on demand on the IWA website as well as the IWA member exclusive Connect Plus platform. And the speakers are responsible for securing their own copyright permission, and any opinions, hypotheses, conclusions, or recommendations contained in the webinar are the sole responsibility of the speaker and do not necessarily reflect IWA opinion. Next slide. So for all our participants today, I would encourage them to introduce themselves in the in the chat box, and to have any questions, general questions. And for questions related to the panelists and the speakers, I would like you to post it on the Q&A box only. Next slide. So quickly going through the agenda for today. So I'll start with welcoming the participants and the speakers and introducing the webinar. Then we have two exceptional speakers, experienced speakers, Professor Ilango and Mr. Rahul, who will each be presenting their own case studies, and which will be then followed by the panel discussion and Q&A, and then with the closing ceremony. Next slide. So just to give a brief background of today's webinar. So this webinar is part of our series, which is Groundwater, the Invisible Lifeline, which aims at understanding how groundwater is perceived from an unseen extractive resource to our dynamic living system. And today's webinar is the third session, which will specifically focus on the technologies and innovation that are transforming groundwater assessment, monitoring, mapping, and decision making. Both the speakers will share their own experiences from both the theoretical and practical experience and point of view. Next slide. So without further ado, I would like to now welcome both the speakers. So our first speaker is Professor Ilango Lakshmanan, who is a visiting faculty at Indian Institute of Technology, Madras, India. So Professor Ilango has over 38 years of experience in hydrogeology. He is currently a full-time visiting faculty at IIT. He has also served as a Vice President of International Association of Hydrological Sciences from 2015 and 2019, and also the President of IAH's International Commission of Water Quality. Our second speaker is Mr. Rahul Bakre. He is the CEO and founder of Udvam Environmental Technologies based out of India, Pune, India. By education, he has done his MS in Mechanical Engineering from Michigan State and has done his Executive MBA at IIM. And he has worked for around 14 years in software and IT, and he has in-depth experience in project management, product and people management in ERP, CRM, etc. So without further ado, I would like to now invite our first speaker, Professor Ilang. The floor is yours.
Hello to everyone. Hope my screen is visible and it is in presentation mode.
Yes, sir, it's visible.
Right.
Can you put it in slideshow? Yeah.
Is it there on slideshow now?
Yes. Thank
you. Hello to everyone. Thanks for the nice introduction. I'll share basically out of several works which we did. I just picked up a few for presentation today. How can we make the invisible groundwater visible? So there are several tools. Some of the tools I'm listing it here. Basically, geophysical exploration methods help us to understand where the groundwater is. Though we don't see with our eye, we make use of certain techniques to understand where is it located. Is it viable to tap an aquifer system with limited amount of groundwater? All this can be answered using geophysical tools. Right? One of the most important tool is the electrical resistivity method, in which what we do is we are going to apply current, as you can see in this picture on the right hand side bottom, right? We apply current between 2 points and the effect of that is studied in between the two. That means we apply current when we measure the potential. As we increase the distance between the electrodes, we are able to understand greater depth of the subsurface, right? That means as you increase the distance, we are able to increase the depth of penetration of current. So this is how we are able to understand whether the formation is saturated, whether it is a clayey formation or sandy formation, where the water table is. Right. So here is an example, right, wherein we are able to understand the spatial variation in a cross section on the electrical resistivity values. That means the horizontal line is the surface, ground surface. This is the ground surface. What you see here is vertically below a long profile. So in a profile, we have now come out with the variation in the spatial variation in a vertical section with reference to the electrical resistivity with the scale given at the bottom, right? So what we are able to get from here, though the water is invisible, we are standing on the surface, but we are able to clearly demarcate a zone which is having very high amount of salinity, because blue color, as you can see here, is the zone which is having the lowest resistivity in this section, right? Whereas this section has got high resistivity, probably they are devoid of any groundwater, most likely they are hard rock formation. So this is how we are able to see what is present below the surface of the earth using electrical resistivity method. Then the other tools are ground penetrating radar, which is often used to study the shallow subsurface. Here are the two case studies in which we had deployed this ground penetrating radar tool to understand the subsurface beneath a river bed, right? Here, what you see is a river. The river flows this way, right? Wherein there was a check dam to be constructed to mitigate the issue of seawater intrusion just north of the city of Chennai. Before the commencement of the site selection itself, we did several traverses to understand the location where we don't have any confining layer very close to the river bed. That means, so only then a recharge structure will perform better. For that, we had deployed ground penetrating radar. Right. Similarly, at another side, the need for improving the groundwater quality, since it has completely saline seawater, wherein a percolation pond with a shaft was tried to identify a suitable site. The ground penetrating radar can be a ideal tool to understand the subsurface characteristics. The limitation, however, is it cannot go beyond 25 meters below the surface and below ground surface. So this is an ideal tool for locating recharge structures. Another major tool, which is very popular since last 1 decade, which is surface nuclear magnetic resonance imaging. In this method, a magnetic field is generated using a transmitter. The effect of transmission leads to change in the way in which the protons are oriented in beneath the surface of the earth due to the external magnetic field. As and when we stop the application of the magnetic field, these protons realign themselves according to the Earth's magnetic field. So during realignment, it produces some signal. That signal is measured in using this surface nuclear magnetic resonance imaging. The greatest advantage is these protons are present mostly in water present below the surface of the earth. Hence, indirectly, we make the groundwater, which is invisible, visible using the surface nuclear magnetic resonance imaging. In fact, this is the only method which directly helps us to identify where the groundwater is below the surface of the earth. There are several techniques, right? That means we measure the data by varying the generation of magnetic field over the surface of the earth and study the response of that. And we can also do what is known as a inversion technique, wherein we assume certain subsurface model. For that, we produce the signal, then we compare with the measured data. By doing so, and there is also an option to understand about the water content present below the surface of the earth. Due to the fact that the water molecules are able to move freely in zones where the porosity is considerably moderate. That means if you take a sandy formation, the water is able to move very freely, though porosity is high for clay formations, wherein water is held so tightly, wherein they won't be able to spin as I have indicated in this diagram. Hence, with the help of this, we are able to demarcate which zone has got movable water, which zone has got immovable groundwater. That is the advantage of this particular tool. So these are all some of the important geophysical tools that help us to understand the subsurface. Today we are heavily dependent on satellites for everything, right? One such tool is the GRACE mission. Since the year 2002, we have this two satellites going around the earth in the polar orbit that help us to understand whether there is any gain or loss of groundwater on the surface of the earth. There is also another set of satellites which are sending radar waves, right? These radar waves touch the surface of the earth and then they get reflected or refracted back, using which we are able to understand the elevation difference, whether there is any land subsidence. These two data can be synthesized to understand whether over withdrawal of groundwater is causing land subsidence. So these tools are now available, right? Especially GRACE data is free, whereas Sentinel data we have to pay and get the information, right? Here we have made use of GRACE data to understand how efficiently it is able to predict the groundwater head in and around Chennai region. So what we have plotted both the measured groundwater level along with the GRACE derived groundwater storage. There seems to be very nice correlation. Similarly, with respect to time, here you can see the blue line is the blue, that is gravity measurement, that is GRACE derived value, and the red is the measured groundwater level. There seems to be a reasonable comparison, except for certain years towards later, which is attributed to seawater intrusion. Right. Similarly, land subsidence, as I told you previously, can be estimated using synthetic aperture radar satellites. Here, there is a tool called SARScape. This tool helps us to understand the land deformation, since the satellite goes over the same site at least on once in a month's time. Suppose if you take a data after a gap of 2-3 years, we will be able to know whether the land surface has deformed, whether it has emerged or whether it has witnessed subsidence. Right here is an example from Kolkata city, wherein you can see it shows the land surface is going down with respect to time. This is a bit old study from 2003 to 2010. We carried out this study using the data from 2003 to 2010. That corresponds very well with the measured decline in piezometric head. So here too, the white lines here indicate the piezometric surface, which is the lowest here, where we have witnessed highest amount of land subsidence. So this is another tool to rapidly understand the variation in the land surface. Geographical information system, right? Using any of the tools here, we have used this particular tool to understand the variation in the groundwater recharge potential zones for southern India, right? In which we had used AHP technique, which is nothing but a multi-criteria decision making, wherein we fix up a goal. That means the goal here in this case is differentiate the entire southern India into highly potential, moderately potential, poor, and very poor for recharge, right? So by assigning different criteria, for example, geology, soil, slope, and so on, we can come out with different alternatives. So using this tool, we had identified groundwater recharge potential zone for entire southern India. Over there, we had the novelty of this study is over there, we had also identified groundwater recharge potential as well as groundwater potential zones, right? So we need to integrate this, right? Whenever we plan for any new managed aquifer recharge structures, we need to identify poor groundwater potential area wherein recharge potential is very high. Right? This is another tool. Using the same multi-criteria decision-making tool, we had selected ideal sites for recharging groundwater in Bangalore city. More than around 10,000 such recharge wells were constructed in Bangalore city, making use of the same technique. So we could also get a visible improvement in groundwater level as and when we completed the construction of these 10,000 recharge wells. There are several tools that require for groundwater monitoring. We use several tools in one of our case study involving construction of a percolation pond, which I had indicated previously, wherein we did a ground penetrating radar. A percolation pond was constructed to improve the groundwater quality for supplying water to a small rural community living there. The entire area is highly salinized due to proximity of this side to the sea as well as the backwaters, right? Wherein we constructed a percolation pond. In order to understand the efficacy of this percolation, we had also drilled 4 piezometers adjacent to that, and these were heavily instrumented using several advanced automatic weather station, and also multiple probes to understand the groundwater potential in the pond as well as a nearby well in all the piezometers, right? So here, this research was published as a part of this book published by IWA. Those who are interested can have a look into this for more details. And one of the common problems which we face, especially after severe rainfall, right, extreme event, suddenly the ground surface gets flooded, right? And the water table is somewhere here. This is the groundwater table, but the ground surface gets flooded and leaving lot of air entrapped between the saturated or flooded surface as well as the saturated zone. Due to the presence of these air bubbles, water is unable to get infiltrated into the groundwater. Though we had plenty of flood waters at the surface, they are not really benefiting groundwater recharge due to the entrapment of air. We thought of how about providing a small tubes in the unsaturated zone so that when during floods, the air which got entrapped due to the pressure of flood water may escape through this. So this concept was presented to the Ministry of Science and Technology. They funded a project. So we did several experiments in some sand tanks, as you see here, with some moisture sensors kept at frequent distance from the surface, right? And we had also put an automatic water level recorder to study the effect of this flooding. Then we had also carried out some field experiments. The experiments support that the presence of vent, for example, this is 1, 2, 3, and so on, help to quickly recharge the groundwater. This technique is able to overcome the problem of entrapment of air, right? We had also filed a patent of this technique. Then coming to artificial intelligence and machine learning in groundwater, there are a number of researchers who have very efficiently used AI and ML tools, especially for predicting groundwater level as well as groundwater quality and groundwater recharge. Right. So these are all the popular themes in which people have applied the application of artificial intelligence as well as machine learning. Most of the researchers have used these tools to achieve their objectives. Right? I'm just presenting two examples. In one example carried out in Germany, the authors have put into use of machine learning to come out with forecasting of groundwater level. So they have achieved a reasonably nice results with merely 17 monitoring wells they had, but they had a long-term data from 1967 to 2015, and they considered three important variables. One is temperature, precipitation, as well as humidity. They had made use of three different machine learning or AI models, and reasonably all the three performed well, whereas this one achieved very highest amount of NSE as well as R square. CNN is also not very much lagging behind. So these tools nowadays are becoming very popular to predict groundwater level, as you can see here, right? Both observed as well as predicted, especially by NOx. They are more or less going over each other, right? And here is the performance of the model. So the key findings is, though all the models performed reasonably well, this model seems to be outperform the other two, whereas CNN is also able to give a reasonable kind of results. And we had also used something similar to what we had seen previously to predict groundwater quality in one part of India, in Karnataka, right, wherein we have been collecting groundwater samples once in 3 months for a period of about 4 years from over 50 wells, for which we had applied machine learning coupled with ant colony optimization tool. As you can see here, let us not go into depth. This is published in this. Details are available in the paper which I am giving at the bottom, right? What is interesting is we use nearly 70% of our data for training, then the rest of the data was used to test the results of the model. Since we had observed the groundwater quality with regard to major ions over 50 wells, every well we had measured about 10 parameters such as sodium, chloride, potassium. I am just showing you the results of couple of them, right? In one particular well, I'm showing similarly we have results of 50 wells. You can see reasonably the orange color line or the saffron color line is the model predicted and the blue is the measured value. There is a reasonable comparison between both. And also here I'm showing you for uranium concentration, which is very important. So there is a reasonable comparison between the model predicted as well as the observed value. Then we also checked whether 50 wells, 50 different models predicted the concentration, and then we came out with a inverse distance method to extrapolate the concentration over the entire area. Then we compared that this left hand side green one is observed and the right hand side is the model predicted. There is a reasonable comparison. So these models are able to very nicely predict the groundwater quality. Right? Though we are using several other contaminant transport models, this machine learning tool seems to be a very good way to estimate the groundwater quality. There are also several other digital tools. One such tool is a popular tool is the water evaluation and planning tool, which we deployed for the city of Chennai to understand, to forecast the unmet demand in water supply, right? Considering the expected population growth in future, right? If according to the estimated population growth, suppose the demand, if it increases, using this tool by considering different sources, we will be able to forecast the unmet demand. So here is the demand, unmet demand, right? On the y-axis, you have the unmet demand and the x-axis is the time axis, right? Time axis. And we played with the model by considering different rainfall patterns. Suppose if you have excess rainfall every year, suppose if you have normal rainfall every year, if you have deficit rainfall, how much will be the unmet demand? Suppose if you put forth of used water, let us assume 200 mld of used water is put into the supply chain, how we will be able to meet the unmet demand? Details are available in this paper. So this is how WEEP model can be used. And of course, groundwater models are excellent tools to forecast or run scenario analysis of different, including engineering solutions. In this case, as I had told you previously, 15 check dams were constructed across these river basins located just north of the city of Chennai. Even before the commencement of construction of these check dams, we estimated the possible impact of these check dams in this area using this numerical model. Then we had also run the model to forecast different climate change scenarios. So what you see here is the impact of this, right? To conclude, we are currently working on a major digital twin. Digital twin is nothing but replicating what exists in nature into a computer-based system with real-time analysis and also people's participation, right? Wherein we are coupling several models. It is a collaborative project between India and Delft. That is it. Thank you very much for your attention.
Thank you so much, Professor Elango, for that detailed description about the tools and the models that we can use for groundwater mapping and assessment. So thank you so much for sharing your insights, and we will take up the questions in the panel discussion. So now I would like to invite our next speaker, Mr. Rahul Bakre, to discuss more about his work in the in technologies and innovation and groundwater. So over to you, Mr. Rahul. Thank you.
Yeah, thanks for this opportunity, Afia, and welcome all to this webinar. I'll quickly share my presentation. I hope it is full screen.
Yes, sir. Yes.
Yeah. So the topic given to us is basically making the invisible visible, the technologies for groundwater management. I would like to go through various types of problems, various types of issues faced by groundwater, and I would like to discuss on practically what and all we do to basically give solutions to the problems what we are facing. So, for example, India is the largest user of groundwater. It has around 8 crore, that is 80 million existing bore wells and open wells. And through that, we are overexploiting groundwater to a great extent. So much so that farmers are committing suicide. Women have to walk faraway places. Even water has to be applied through tankers, and water quality is becoming a major issue. In some cases, uranium, chromium has started coming in groundwater as such. So, groundwater in the Indian context is one of the major water sources. 80% of India depends on groundwater as such, and this is the problem what we are facing. So when we map the water utilization flow, we realize that basically there is something called as natural resource, and the source needs to be developed, treated, then basically it's used, and wastewater is generated and wastewater is treated. And that is something which is the kind of water utilization flow. And from source development to waste treatment, is there a lot of crowded engineering product space. So we provide solutions to the sustainability of the natural resource, may it be groundwater, surface water, or rainwater. And we use a lot of IT, IoT, robotics, mobile technology to solve people's problem on the ground as such. So why we need to think about groundwater? Because groundwater is invisible, it is unseen, hence ununderstood, unappreciated, but it is creating tremendous amounts of problems, and that's why we should learn about groundwater. Water, because of water, groundwater, basically droughts and desertification is happening all across the world as such. Groundwater also is one of the reason why deforestation is happening. So a lot of afforestation is also happening because of climate change. The recharge regimes are changed, and because of the recharge regime, because of the change in the basically rainfall patterns, intensity, etc. It's also creating a lot of deforestation, and as I said, the droughts, as a matter of fact, desertification. And afforestation is a solution for that. But currently, the afforestation doesn't take into account the groundwater regimes, as a matter of fact. And actually, that is something which people certainly should know, where to plant which kinds of trees, depending on the hydrogeology part of it, right? Typically, based only on the agroclimatic zones, the afforestation is done. But probably for the plants to basically live, sustain, and move on and grow, one needs to understand groundwater hydrogeology. Rivers are drying up, as we know it. Many places rivers flow only during the rainy season, as a matter of fact. And during the non-rainy season, there is no water because the base flows have dried up. And why the base flows have dried up? Because water in the unconfined aquifers in many parts is used for pumping at a much a faster rate than what nature can replenish. And because of that, the base flows are reducing, and because of that, rivers post monsoon are not providing any water to the civilizations as such. Water also is a major problem because when we construct a road, when we create a escarpment, that creates a weak zone for the hydrostatic pressure to get applied, and that's what creates the landslides. Landslides also are caused because of the friction between the what between the different particles, and the pebbles and stones gets reduced because of too much of water basically getting seeped into location. So unfortunately, many such construction activities, may it be houses, may it be roads, may it be even watershed kind of treatments are done without any understanding of hydrogeology, that creates more problems than solving the problems as such. We have seen in my near my city, village which was entirely swiped away by a landslide, because unfortunately, because without understanding the hydrogeology, a huge tank was constructed upstream, which was a farm pond, and that farm pond during a very torrential rain evening basically succumbed to the water, and basically that water created tremendous amount of I would say force on the slopes, and basically the entire village was flooded, and entire village was actually buried under the mud. But because people didn't understand the hydrogeology when they considered constructing that farm pond in that location, at the same time, we also have seen many places sinkholes happen. As we know, sinkholes also happen because of not understanding the underground water regimes which are out there, and because of that, many places a lot of basically destruction happens. Water also, groundwater also is a problem which causes foundations to fail or foundations to topple over, and the households also kind of topple over. Land subsidence is another major issue which is faced by many people. In California context, 9 meter subsidence is seen in some places. There's a tremendous amount of subsidence creating tremendous amount of problems to groundwater assets. So what I'm trying to say is that again, these are the basements which are flooded during every rainy season in India, because again, hydrogeology is not taken into consideration while constructing those basements as such. So hydrogeology is very important, critical, and crucial, but unfortunately, it is not taken into consideration. It is taken certainly into consideration while mining, but there also in many places flooding of the shafts and mining shafts is already seen, as a matter of fact. And lastly, groundwater also needs to be considered while developing the sanitation infrastructure, because in the Indian context, for example, pit type recharge systems, pit type toilet construction creates tremendous amount of problem in the rainy season, because a lot of that water becomes groundwater and gets transported downstream. So for even as something as simple and as distant as sanitation also needs to take into consideration the hydrogeology as such. So there are three major gaps in groundwater domain what we have seen. First of all, awareness and education in general masses doesn't exist. People don't know. They have very vivid imagination about groundwater, whether is there any stream flowing underground, or there is a pond, or there is a sea of sweet water, but nothing of that sort exists. But unfortunately, people have that kind of a visualization. Second is that people want more and more supply for their day-to-day activities and their economic activities as well. And people want more and more water, and water which is generated through groundwater supply, it is not managed properly. So the demand management also needs to happen, because a lot of water is given to plants, especially in agriculture, in basically in furrow and that kind of a way, and because of that, a lot of water gets lost in the evaporative losses as such. So we work in awareness and education. As I said, awareness education is a very important part of it. We have developed a gamified visualization for education and awareness generation on groundwater behavior, because as I said, giving people animations, people are not able to imagine. So we have developed this see-through model of groundwater behavior, on which kids or even adults can basically put rain on top of it, and how the groundwater behavior happens. It can be simulated through gamification of education kind of a methodology, where difficult to visualize 17 to 18 scenarios they can generate by themselves through play, and by that they are able to understand the groundwater behavior. So because it is gamified, there is a better retention of this understanding in their brain, and long time recall happens. So that's what we have seen and observed in the Indian context as such. We also work on supply augmentation. We have developed a patented smart rainwater harvesting technology that recharges and revives existing low yielding or dry bore wells, in which we basically do inter-aquifer transfers, obviously with due scientific understanding. So when the rainfall happens, the topmost part of the earth system, there is an animation. gets filled up very quickly, but through different hard rock layers for the water to reach up to 200 feet. For example, it takes hundreds and thousands of years. And from there to reach up to, let's say, 600 feet, it takes millions of years. So is the slow nature of groundwater recharge, as a matter of fact. But when we drill a borewell, the driller makes one hole up to, let's say, our borewell is 600 feet within one day. And what we see borewell on the surface actually is a casing pipe, which is impervious PVC MS steel pipe. And that doesn't allow any debris to fall in the borewell. But along with that, the replenishable water from the topmost aquifer also doesn't enter the borewells. So borewells typically get water from the lower aquifers whose natural recharge is very low and slow, but our electromechanical pumping is very fast. And because of this imbalance, typically initially good yielding bore wells slowly become seasonal, and many of them they go dry completely. So in bore charger technology, our trained hydrogeologists undertake angiography of the bore well, and we put our patented tool after in the bore well, and we perforate that casing pipe at hydrogeologically appropriate depth, so that only filter water will come in the bore well, and it artificially gets injected in this bore well, and it reaches 600 feet within few seconds, what it takes millions of years, and it gets readily stored in those greater depths. So this is kind of a vertical smart rainwater harvesting technique what we have been able to develop, and we have implemented more than 7,000 bore well recharges, and we have seen tremendous amount of traction. So these are some of the classical successful implementations, as a matter of fact. What are the real world problems faced by people, and what's the impact of bore charger kind of a technology? Nabi Saab, a farmer whose agriculture income was very low because his water level used to go down to 450 feet every year. Because of bore charger technology, his agriculture income rose by 85% within 1 year itself, because he started getting 6 hours per day water compared to 1 hour per day during summertime. Shivaji Suryavanshi, a sarpanch, a local body chief, he is pumping drinking water, village drinking water borewell was pumping only 30 minutes per day, and his village was insecure. After bore charger implementation was done, this pumping increased to 4 hours per day, and his village became water basically secure. Rakesh Koti, an urbanite, he had 15 minutes per day worth his borewell water. It increased to 3.5 hours per day, and his completely dried up borewells also started yielding because of this inter-aquifer transfer, as a matter of fact. And because of that, he saved 600,000 rupees a year towards tanker water supplies as such. So overall, the socio-economic and ecological impacts of bore charger are quite clear. We are able to increase the recharge rate 4 to 20 times, anywhere between 200,000 to 8 million liters of rainwater gets added to the borewell every year. This increases supply by additional 1 to 6 more months, and along with quantity and quality improvement, we have seen 95% plus success rate we have seen, and we have reduced the vulnerability of farmers to weather shocks, and we also have reduced a lot of tanker water supplies as such. So when we are analyzing this problem about deeper aquifers not getting recharged, and that was one of the reasons why borewells go dry, we also thought why the borewells go dry in the Indian context, especially, is because the location of the source is not identified properly scientifically. Typically, in the Indian context, diviners, which are coconut divining or rod divining, and those sorts of things are used to basically find a spot by using divining methodology. But unfortunately, that is highly inaccurate. Only maybe 20% accuracy is there. So we have developed this source identification and aquifer mapping kind of a technique, which Professor Ilang also mentioned, vertical electrical sounding. I won't go into deep about this whole part of it, but this is the topmost side of the image. You can see it's a 5-acre land on which this vertical electrical sounding survey was done, and the red, blue, the red and pink zones are the zones which are highly compact in nature. Green, yellow ones are having some moderate porosity, and the dark blue zones are the ones which are having very high porosity and good potential to find water. So now, how do we use this kind of an ultrasonic or a kind of a cross section of the Earth system, which is invisible to our naked eyes? Is that when a diviner gives a borewell location here, obviously this borewell won't fetch much water, because the dark blue zones, which are highly porous in nature, don't have much interface with this borewell. But if we would have done this scientifically, we would have shown this as the location which would yield much, much more water. Same is the rainwater harvesting pit. If the rainwater harvesting pit is done here, this yellow green zone doesn't have that much amount of porosity, so it won't be that efficient. But if we do this through scientific methodology, we can use this location for better rainwater harvesting. Same is for the location of open well as well as a recharge pond structure for a for a watershed. We have seen many places. I myself have evaluated many watersheds where the end user says that, sir, in February also see so much of water in this percolation pond, but you cannot call it as a successful implementation because the fact that there is water in that tank till February means that it has not percolated. So you have created a storage pond as compared to a recharge pond. And we have worked with many CSRs, many NGOs, many government programs, and we have first studied the watershed with the help of hydrogeology, with land use, land pattern change, slopes, and so many other factors we take into consideration. And based on that, we do aquifer mapping of the entire space, and then we provide scientifically correct, accurate, effective and efficient location for the structures which are supposed to be constructed there. So groundwater is extremely important. As a matter of fact, we also use geomagnetic technologies to understand the potential to find water underground as well. Lastly, from the demand management side, we have developed this Jalstar scientific groundwater measurement and prediction technology, which is basically a piezometric sensor, which is IoT enabled, which gives real-time visualization and also can provide predictive analysis. So just to give a classical example for a farmer or an end user for one sensor or one borewell data, we can see when the pump starts, the water level is here. After some time, the water level goes down with the pumping, and when the pumping ends, the water level attains another depth, right, which is much lower than the earlier depth. But after the pumping start, the water level also recuperates slowly. Now, this is for one bore well, but within this bore well, we are able to provide what's the volume of pumped out, water pumped out from this. And with this, the farmers are now able to undertake tremendous amount of informed decision making, such as next crop, which crop to take, what cropping area, cropping variety, so on and so forth. And based on that, many farmers have increased their income. Many farmers also have been able to take additional crops for their during summertime. Many farmers have been able to a good amount of animal husbandry because of this kind of a advisory and input which is given. Now, the core offerings are we are able to provide very high frequency data, real-time visualization analysis, and most importantly, the advisory on data analysis and prediction. So as you can see, we have this data from November 24 to January 26. The pumping for the domestic use of this bore well was clearly showing certain pattern, but during monsoon, the recharge happened, and again the pumping happened for the domestic use. Now, with the help of a lot of contiguous data, we have been able to now predict the data. So in November 25, when we started prediction, the green line on the right hand side, actually the dotted line on the right hand side is a test and the forecasted water line based on the past previous data. But the green line is something which is quite matching, which is the actual data which we have been able to measure and predict. So the prediction based on AI, ML, and as well as certain statistical methodologies, we are able to achieve a good amount of accuracy. So we are able to provide tremendous amount of input which people are not currently getting, as a matter of fact. But when we look at this prediction over long period of time, we are able to predict water level data as well as predicted quantity and duration of water supply as well. So that's the predictive behavior advisory we are adding value into. With these sensors put in a specific watershed or a village, we are able to develop aquifer health status, which the villagers can see on their big monitor in their Gram Panchayat and are able to see what's the water level and the animation, something like this animation, which they are able to understand. So again, through gamification of the information, we are able to give them better understanding and visualization. And also 3D visualization also can be done with this kind of a contiguous data at a very frequent level. So we have been able to tremendously impact farmers, rural communities, households, industries, as well as NGO, CSR, social impact, environmental impact programs as well. And we are working with governments and regulators as well. So now how do we convert all these things into a scalable model? Is basically we have our regional offices and we are serving the farmer industry townships, which are the real world beneficiaries of our services. But through this model, we cannot scale up. So the idea is by training local youth and converting them into para hydrogeologists, in which they are not hydrogeologists, but they would be able to collect a lot of data on a very frequent basis, and they would be transferring the data to us over IoT, and through automation of our technologies, which would give in their hand, we would convert them into our franchises. So they would be our on-field implementation arm, and through that we would be converting them into franchises, and those are the ones who would provide tremendous amount of affordable, scalable services at that local level, wherein we using IoT and the cloud technologies can do a lot of visualization, modeling, assessment, analysis in our head office, and we would be able to provide advisories to people. So with that, let's recharge, replenish, and revive groundwater, especially for our future generations. क्योंकि जल है तो कल है. It means if there is water, there is tomorrow. Thank you.
Thank you, Rahul sir, for sharing your experiences and deep insights about, especially in the field work and how you have interacted with the different communities and how your product has helped different communities and stakeholders in improving their produce and also their livelihoods. So thank you for sharing. So I think we have limited questions because which means that participants do not have much doubts and they are very clear with both the speakers' presentations. So I would request Mr. Ilango to come on board, and I would now request both the speakers. So I'll just read some of the questions, and then based on your understanding, you can reply or you can give your suggestions. So the first question is for Mr. Ilango. So, dear Professor, thank you for your informative presentation. The question is sinkhole occurrence related to land subsidence? And the second question related to it is, what are the factors that should be considered to assess the spatial risk of sinkhole occurrence?
The land subsidence and he was asking sinkhole, am I right? Sinkhole caving.
Yes.
The land subsidence is a very slow process. That is how we can distinguish sinkhole collapse, right? Even Rahul showed some nice videos, which are all probably due to some issues below the surface, maybe a limestone or a sudden failure in a subsurface storm water drainage, right? They cause something like sinkholes, sudden caving. Right? Land subsidence is a very, very slow process. This is how both can be distinguished. And the second question, I didn't get you.
Yes. So, what are the factors that should be considered to assess the spatial risk of sinkhole occurrence?
What are all the factors that needs to be considered, right? The most important factor is to understand what is the extent of this sinkhole, which is very difficult to estimate. We need to rely heavily on the geophysical tools, right? Including major structures, as he nicely showed in videos, big buildings, without considering the presence of sinkholes beneath, huge structures are being constructed. So the role of geologists is very, very vital. They should first of all test the site using geophysical tools. The geophysical tools are the ultimate one to give us information about the strength of the subsurface. Right? There is nothing else available. I hope I have answered your question clearly, right? If you have anything else, you can correspond with me or with Rahul.
Yes, thank you, sir. Rahul, sir, do you have any pointers to add on that?
So I think certainly, just like Professor Rang also mentioned, land use, land pattern change also needs to be considered. Slopes needs to be considered. Rainfall patterns, especially in the climate change context. Stormwater management, existing and older stormwater management practices have to be considered. Hydrogeologically, what's the strata? What's the certain, maybe certain test borewells needs to be taken, because those are the ones which can provide some sort of a understanding of the underlying geology and hydrogeology as well. Maybe even in some cases, even pumping test needs to be taken into consideration to understand the yield. Some of these things are the things which can certainly a detailed hydrogeological study. If it is undertaken, many of these future problems can be solved.
Great. Thank you. Thank you to both. And the second question is more related to the data part. So the question is, what would be the minimum amount of data in terms of years ideal for ML or AI analysis? And then, yeah, so that is the first question. So if any one of you can go
So,
ahead. Yeah, yes.
we don't have a straightforward answer. For example, in any statistical analysis,
Hmm.
we say at least 30 time data is necessary. The same is applicable here too, right? When we are talking about water in India, we need to at least consider 1 year minimum. 1 year data is necessary. Even 1 year is not really sufficient to understand whether the cyclicity is getting repeated. So I will say, suppose if you are using monthly data, at minimum of 5 year data is necessary, right? 5 into 12, 60 times you have measured, let us say, groundwater level. So 60 times measurement, I will say, is the minimum requirement. Anything beyond that is a bonus. Any model will perform better if you have more observed data.
Thank you, sir. Rahul, sir, do you want to add?
Yeah, so I 100% agree with Professor Elang was that more is the merrier. But in real world scenario, we may not get that kind of a prolonged timeline kind of a data. So there we get as much data as possible, and based on that we can run certain analysis as well as certain modeling which we can build. And in absence of any data, something is better than nothing. So whatever is the data which we are have available, we tend to use that and provide applied solutions to people.
Great. Thank you. So I think now we are getting a lot of questions as well. So I'll take another one. Can we always conclude low resistivity areas as potential aquifer zones?
Not really, right? We are If the resistivity is low, maybe a ore body, or most likely it will be a clay formation. So resistivity should not be too low. If a very low resistivity, most likely indicating clay zones. Suppose if you take a coastal area, maybe like Chennai, you may have sandy formation. Over there, at the lower part of the sandy formation, we would have measured very low resistivity. Over there, it points to seawater intrusion. So we cannot attribute the value of resistivity directly to a formation. So you need to put in your collective expertise to come out with a meaningful interpretation. So in order to refine your interpretation, always it is necessary to go for a couple of test boreholes. Right? No resistivity survey is complete without carrying out 1 or 2 test boreholes to test our interpretation or hypothesis we have made. So, to answer your question straightforward, simply low resistivity zones are not aquifers. Thank you.
Great. So there are another question. Okay, so I think this question might go for both actually. So Weber has asked, the study used many instruments for respective objectives. My question is, are there any proxy exits to complement the outcome, or in absence of availability of any highly sophisticated instruments?
I didn't get you for which study is referring to.
He has not mentioned. So I think commonly, so what we can understand is if there is an absence of highly sophisticated instruments, what are the different alternative ways that we can use for such studies? Yeah.
Absolutely right. Always we need not go for highly sophisticated instruments, right? For example, if you are exploring for groundwater, a mere field work, understanding the formation at the surface, is it a sandy formation or is it a clay formation? Are there any wells? Are there any excavations existing in that area? Right? A geologist will be able to guess even without visiting the site. From the satellite image itself we can come out with some idea about the terrain. A site visit will certainly enhance our idea, right? So we need not always depend on the sophisticated tools to get some simple answers. That is my view.
Thank you, sir. Rahul, sir, another question is specific to you. Acha, do you want to answer this as well?
Yeah, yeah. So
Yeah.
actually, see, the instrumentation need not be sophisticated, because more sophistication, more is the cost, right? And more difficult it is to also basically analyze and all. So I think just like Professor Lango said that for unconfined aquifer, which is shallow aquifer, probably certain existing secondary data or satellite image analysis, vegetative basically indicators. There are a lot of botanical indicators which can also tell you about, especially the shallow aquifers. But for the deeper aquifers, yes, there has to be certain instrumentation applied, and that instrumentation need not be basically sonic or acoustic or something like that, which is used typically for oil field and oil identification, oil zone identification, etc. But simple VES is also sufficient as a matter of fact.
Yes, thank you. And next question is, Rahul, sir, specific to your presentation. So the patented boat charger really sounds interesting, but have you experienced installing it in volcanic formations? And is it expensive?
So certainly, actually, it works fantastically well in the hard rock regions, which are volcanic in nature. Basically, we are sitting on one of the world's largest basalt formations, volcanic formations, and we have seen tremendous amount of impact. We have done more than 6,000 plus implementations for farmers, for households, as a matter of fact, for hand pumps as well, community hand pumps as well, and tremendous impact we have seen. As I said, people have taken more crops. People, the hand pumps which used to get dry in the month of Jan, Feb, now have started yielding water till May and June, solving their lot of problems and reducing a lot of drudgery of fetching water from faraway places. So, yes, it works absolutely fantastically well in volcanic formations.
Great. And I think we'll just take one more last question to Professor Elango. Can flash flood water in urban areas or cities be screened and recharged?
Yeah, certainly. We can go in for some sophisticated stormwater drains, right, which are engineered to filter the stormwater. These are all some of the measures called sustainable urban drainage, but which are a bit expensive to install, but there are successful examples. Which what it does basically is to drain the stormwater which falls on the garden or which falls on the roadways into a small ditch, which has got some sophisticated filtering system which filter the water. The filtered water eventually enters into a stormwater drain or into something like bioswales where the water is retained. Of course, the filter requires maintenance as we do at our water filters at home. Yes, certainly stormwater can be treated in situ and allowed to run into the bioswales or into stormwater drains.
Yes. Rahul, sir, anything to
Yeah.
add? Yeah.
So to answer that question, so certainly why stormwater is getting generated is that because of the anthropogenic activities like construction and pavements and other stuff, right? So I think in absence of that, the stormwater would not have been as huge as what we are seeing nowadays. So in the urban context, a lot of pavements are constructed, concretization is happening, because of which the stormwater is getting generated. Now, the typical wisdom of people is to basically take all the water in a specific premises to the lowermost point in the in the topology and create a recharge structure there. But it's not going to really work, because the recharge capacity of recharge rate of ground is very slow. So the capacity is very high, the recharge rate is very low. So we have to construct many points of recharges in that facility. Just like Professor also said, that in the stormwater drain itself, it can easily be accommodated. But the thing is that it is not one size fits all. One has to first study the hydrogeology. One has to understand the capacity to capacity and the rate of absorption of water and recharge of the water, and based on that the buffer needs to be developed, then filter needs to be developed. But certainly it is not a costly affair if this kind of a study is undertaken first, and then a professional does the hydrogeologically assess the area and does the implementation. I'll give a classical example. In my city, there have been so many people who are civil contractors, and they think, okay, just make one ditch and put water in there, and that's the rainwater harvesting. But unfortunately, there's too much of oversimplification of science of groundwater hydrogeology, which is happening, which is really not good for people, because people are getting fleeced. They are spending lakhs and lakhs of liters of water, lakhs liters, lakhs and lakhs rupees, hundreds and thousands of rupees, but unfortunately they are not getting sufficient output of that, of groundwater recharge, because unfortunately it is done by anybody and everybody, and not by a scientist. It's like, basically, I have a pair of scissors, so I don't become a good surgeon, right? So if really one has to get an effective and impactful solution which will solve the problems, one has to go to a surgeon, and only the surgeon can do the surgery per se, which will save the patient as such. So I think it is very much important and crucial that hydrogeology is given its rightful share and rightful attention by the builders, construction, urban planning, and even rural planning, basically entities, and the policymakers and decision makers as such.
Sure. Thank you. Because of time constraint, we will not be able to take any more questions, but thank you to both the speakers for their, time and support for making this webinar a success. And I hope that we'll be able to answer all the rest of the questions, and we'll share it with the participants in the coming weeks. So thank you again to both the speakers for sharing their detailed insights and their experiences in assessing groundwater. Now coming back to the upcoming events in IWA. So all those participants today, so we have next webinar coming up on 19th August, titled Guardians of Water, Indigenous Women as Knowledge Holders and Water Stewards. And if you're interested, you can click on the link below. Next slide. Then we have another exceptional webinar, which is focusing on water sensitive design and planning, tools and nature based solutions, which will happen on 27th August. And you can click on the link below. And of course, we have our IWA World Water Congress and exhibition in Glasgow from 4 to 8 August, and registrations are still open. So I would encourage all to visit the website. Next. And then for all those interested in the digital aspects of water, we have our upcoming Digital Water Summit in Istanbul from 24 to 26 November, and registrations are open. And last but not the least, so if you're not an IWA member, you can scan the QR code here and become our member to experience many such webinar and knowledge activities. And for all the new members, we are providing 20% discount on our membership fee, which you can use the discount code as mentioned in your screen. Next slide. Yes, so I think I would like to thank all our participants who have joined from across the world to make this webinar a success, and to listen to our speakers and to actively participate in the discussion. And I would encourage you to attend all our webinars, and see you in the future. Thank you so much. Thank you to all the speakers.
Thank you. Thank you very much.
Thank you. Thank you very much.
Thank you. Bye bye,
Bye.
Rahulji.